Hello, everyone. My name is Quan Liu, a staff scientist here at Q-Chem Pleasanton. It's my pleasure today to introduce our speaker today, Professor Martin Hagorn. Martin is a Kenneth Pitzer Distinguished Professor of Chemistry at the University of California at Berkeley and the scientific advisor to Q-Chem. Martin's research group centers on development of new electron structure theory methods and their implementation as efficient computer algorithms. He is recognized with many awards such as Medal of International Academy of Quantum Molecular Sciences 1998 and his selection to American Academy of Arts and Science 2011 and the American Chemical Society Fellow 2012, member of National Academy of Sciences 2015, last but not least, the Schrödinger Medal of Watak 2020. So without further ado, I'm going to turn this over to Martin.
All right. Thank you very much, Quan Yu, and hopefully you can see my screen. One thing that Quan Yu didn't say is that I've been involved with Q-Chem for actually just a little over 29 years now. So it's been an exciting, long journey, and as you'll hear about today, one that is very much in its most vigorous phase right now. And you know, I represent kind of a large Q-Chem community, and so for sure I don't actually know everything that's going on about Q-Chem 6. I'll try and tell you what I do know, and maybe and hopefully that will hit most of the key points. So we think it's the dawn of the next generation, and I'll give you a little bit of background to begin with, then walk you through some of the key features that are implemented in Q-Chem 6 that are appearing. You know, we do this time-based release stuff, and so key features appear constantly. And then finally, we'll finish up with a glimpse of a few things that lie ahead. Of course, chemistry and computational chemistry is enabled not just by the algorithms and the methods that I'll be spending almost all of today on, but I should spend just a minute reminding everyone about the fantastic growth of computing power. So this is some information from the top500.org site showing the growth of supercomputer power. The #1 supercomputer in the world is in mustardy color here in the middle, the number 500 in dark blue, and the total from integrated total 1 to 500 in green, and the units of those that only a theoretical chemist can love, the number of adds and multiplies per second, which advanced from when Q-Chem was first founded, being just below the teraflop level to then climbing to the petaflop era, and we are now approaching the exaflop era. And since I'm at Berkeley, I would be remiss if I didn't point out that last year, the Perlmutter supercomputer was installed at the NERSC Supercomputer Center, which, by the way, has a Q-Chem license, and it contains some 1,500 mixed GPU-CPU nodes and achieves a speed of 64 petaflops per second. But neither I nor you nor anyone can get all of that 64 petaflops per second because it's serving the entire nation. So really, in a way, what's more relevant is what can a typical research group in either academia or industry easily afford? And that's those are server boards. And the state of the art in server boards in 2022 is quite exciting as well. It's typically you know, somewhere between 64 and 128 cores, a cost of typically less than you know, on the order of $5,000 to $15,000. And capable of performing at up to about 4 teraflops per second, which is that next horizontal blue line there. And if you sort of run across there, you see that this matches or beats the world's #1 supercomputer center from circa 2001 or 2. So really, what one has in one's hands or in one's research group to do computational chemistry with is extraordinarily powerful. Okay, so then what about Q-Chem? Q-Chem provides the software to enable you to utilize hardware like that. And it's a journey, and you can read about the sort of summary of the Q-Chem 5 era in this paper, this mammoth paper that we put together last year. And it really does take a village to build a software package, but the village has to have leaders, and the leaders are really the 8 scientific programmers at Q-Chem, who I'll introduce briefly on the next slide. Their roles are to try and coordinate development and centralize the difficult tasks associated with managing a complex software project like Q-Chem. Q-Chem is more than 10 million lines of code, I believe. And at the same time, we allow a community of well over, on the order of 200 active developers to check in, check out, update. So this is a key role for the Q-Chem team. And as you'll hear about during the rest of the talk, the Q-Chem team also takes on leadership roles in developing critical software infrastructure for either performance, capability, modernization, or even just even the fundamental infrastructure. And then that giant list of names you see for Q-Chem 5 is associated with our broader Q-Chem community. And to me, one of the reasons why it's an honor to give this talk and a duty to have a very short sleep last night because of preparing it is to represent this community that has evolved around Q-Chem. And the Q-Chem office, as well as the Q-Chem leadership, really has done a great job of pulling this together. So our academic affiliates, which is some 20 fully committed groups and at least another 20 loosely associated groups, basically they innovate and use Q-Chem as their development platform. And we are an open platform in the sense that anyone who's listening who might want to join Q-Chem as a developer is welcome to, if you simply purchase a regular Q-Chem license, which costs a fraction of one node. So certainly is affordable if you are serious about this stuff. And our Q-Chem developers are also often responsible for being good developer citizens. You'll hear a bit about this as we go on, so this is basically how we roll. And the leadership roles, as already foreshadowed, are really the Q-Chem office team. And so I want to highlight briefly everyone on the team. Evgeny Ipanovsky is our Chief Operations Officer, and while I won't put his name on every slide, I could have, because he has his hands in almost everything at Q-Chem. But because he's then supervising and managing so many projects, he's kind of spread out over everything. Eric Bergquist, you'll hear about later in the context of archiving and journaling. Xintian Feng, you'll hear about in terms of high-performance computing and DFT. Peter McLaughlin, you'll hear about in the context of a new geometry optimizer. Shannon Hauk, you'll hear about in terms of our future product and module. Andrew Gilbert develops the IQmol visualizer and also is contributing to journaling. Quan Yu Liu is in charge of customer support and also hosting webinars. By the way, Shannon also manages Q-Chem's website. Yu Zhang is doing research on computational spectroscopy, amongst other things. You'll hear briefly about that. Then at the office, the people that you may interact with if you're actually looking to ask questions about purchasing Q-Chem, the front lines are manned by Sarah Taniguchi and Mary Sue Flick, who both do a wonderful job. Academically, we are spread out all around the world, and I won't belabor the list except to say that all major countries and continents are represented, apart from possibly Antarctica. and that's the strength of our development. You can kind of get a measure of the usage of Q-Chem. Well, one sort of very academic measure. I am an academic. I must be true to my roots. The citations for the Q-Chem publications, which appear as these purple bars, the citations per year, not the cumulative citations. You can see them growing steadily as the years pass, and so we are steadily having an impact on chemistry through people using Q-Chem to do their target applications. How do we work in terms of releases? Well, fundamentally, as Evgeny took the reins at Q-Chem after he switched us over to time-based releases. And so we do one major time-based release per year. The last one was roughly a year ago, Q-Chem 5.4. And then we do two minor releases following later each year. So 5.4.1, September of last year, 5.4.2, December of last year, cleaning up issues, loose ends, features that didn't quite get in, but fundamentally it's time-based releases. And while if you buy Q-Chem, you get a copy that lasts forever, we do encourage you to purchase the Q-Chem maintenance plan, QMP, so that you get each new upgrade as it's released. And so today I'm describing the generational release, the version 6, that represents the first new generation of Q-Chem for 5 years, and it's likely to then go through at least 5 yearly iterations itself. And so that's basically an overview of Q-Chem and how we release. And so that's maybe enough background to now let us dive into what you're hopefully all here for, which is to hear a bit about what's new in Q-Chem 6. And of course, really, this will be a very incomplete list, because if you listen to the webinar that I gave some 5 years ago on Q-Chem 5, lots of the key features that emerged in later releases of Q-Chem 5 were not even described in that webinar. So we roll ahead each year with these time-based releases. But this is the catalog of the things that I'll spend the next part of the hour discussing. And we'll be leading off with the fact that roughly 95% of quantum chemistry calculations are density functional theory calculations. So Q-Chem pays a great deal of attention to density functional theory. And I want to highlight 3 aspects: new capabilities in terms of functionals and the best and broadest range of functionals, unique analytic frequency capabilities, and algorithmic improvements. Of course, we occasionally take a peek at our rivals, and I guess the rival that we might compare against in the US is Gaussian. Q-Chem, in fact, originated as a group of developers splintering off from Gaussian in 1992, the end of 1992, so almost exactly 30 years ago. And Q-Chem's past president and co-founder Peter Gill began writing code from a blank slate in 1992 that has eventually grown into the Q-Chem of today. The Gaussian of today gets is our benchmark in some ways, but really quite a few of the key things in Q-Chem are missing in Gaussian these days. In particular, all of the highest performing density functionals, the Van der Waal corrected combinatorially designed density functionals, are still missing from Gaussian, but they are available in Q-Chem. And if one then takes a look at functional assessment grouped by rungs of the metaphorical Jacob's ladder that describes density functional theory accuracy versus how many physical inputs or descriptors are there, you can see that the lowest rung 1 is not even on this scale. This is a set of benchmarks from Stefan Grimmer's group and Lars Gorig. And you can see that from rung to rung, the best functional at rung 3 comfortably beats the best functional at rung 2. The best functional at rung 4 comfortably beats the best functional at rung 3. The best functional at rung 5 comfortably beats the best functional at rung 4. And none of those best functionals can you run in Gaussian. And so we note that DFT is systematically improvable in a statistical sense. And we furthermore note that the functionals shown in green are functionals that are Berkeley developed that you cannot run in Gaussian. One of the things that is brand new in Q-Chem 6 is the ability to do analytic frequencies for those functionals. And in fact, there is no code anywhere in the world that you can get that will do analytic frequencies of VV10 containing functionals except Q-Chem release 6. And so the developers for this immensely technically difficult project are Jiaoshu Liang, a brilliant graduate student in my group, and Xintian Feng, a brilliant developer at Q-Chem. And the last bugs, we believe, were found last week in large jobs, so those are the worst bugs to find. The analytic frequency offers all the advantages you would expect. A significant speed up to 5 times speed up over finite differences, similar to other analytic frequency methods. And importantly, the VV10 terms are not normally rate limiting, thanks to very efficient thresholding of the double numerical quadrature that's involved. This is a very difficult project and we're really excited about it. And of course, analytic frequencies offer precision advantages as well as efficiency advantages. And it's not just, the efficiency advantages are leveraged through excellent parallel scaling. The new code achieves roughly 80% efficiency on the VV10 terms out to 32 cores. So this scales very well in an OpenMP environment. So we're very excited about this. It's a significant feature of Q-Chem 6. Let me then move on to talk about parallel scaling in general. And I want to point out that part of the Q-Chem community is, I mentioned briefly before, this good developer citizens. There was perhaps no better developer citizen than Michael Vormit, a senior person in Andreas Droy's group in Heidelberg, one of our major development sites. And Michael tragically lost his life in a holiday accident, and we have created an annual award, the Vormit Award, that recognizes outstanding Q-Chem developers, and Xintian is the 2022 winner of the Vormit Award, and so we congratulate Xintian. You can view his webinar online that has a lot more detail about the things that I will just summarize very briefly here. But a major reason for recognizing Xintian is his key recent work on optimizing parallel efficiency and also, as you'll hear about, CPU efficiency in DFT calculations in Q-Chem. So for our little example here, we'll consider a heptamer of naphthalene, and we'll be using, well, fairly standard Intel Xeons. We'll be using the best rung 4 functional, omega B97M-V, in a triple zeta polarization basis. That's 2500 basis functions. And here is an indication of what Q-Chem's standard DFT in version 6 can do. So this is strong scaling for a fairly large job, and the different components of the job are broken down here. The VV10 component gives you the best parallel efficiency. The worst parallel efficiency by a modest amount is the J component, followed closely by XC, and then in purple here is the SCF, which is over 70% efficient out to 32 cores. So you can really use Q-Chem's OpenMP capabilities on modern nodes with confidence and without generating more waste heat than necessary. So that's a major accomplishment. It's kind of a starting point. It's not a stopping point, though. Another key piece of Xintian's work has been the implementation of a fresh implementation of resolution of the identity or auxiliary basis set methods for DFT. So new numerically stable and also scalably parallel implementations of RIJ and the OC-RIK method that in fact was a Berkeley development in efficient RI methods from back in 2015. But in my group, we didn't grapple properly with building the parallel infrastructure. So anyway, this is just 2 equations to remind you what's going on here. The normal atomic orbital integrals are the Greek indices mu and mu. an RI basis, something like 2 to 4 times larger are the capital indices, and we then reduce the 4 center 2 electron integrals to linear combinations of 3 and 2 center integrals. And Xintian has implemented both an in-core and an out-of-core or on-the-fly algorithm. And let me just give you some indication of what performance you can see when you get a chance to run these yourself in Q-Chem 6. The in-core speedup for the same example, I think it's actually the naphthalene hexamer, not the heptamer this time, but same functional, same basis, gives you an in-core speedup for the total SCF, so all parts, of 7 relative to our default 2E4C code. And that's, if you can stick things in memory, that runs out of steam roughly about the hexamer of naphthalene. And then you need to go to an out-of-core algorithm, and that still gives you a speed up of 3.4 or so on that same example. So this is very, very useful. The parallel optimization is one of Xintian's many current projects, and right now he, or not right now, last week, as of his Vormet Award webinar, he reported roughly 20 times speed up on 32 cores. And as you'll see if you listen to that webinar, he thinks more is possible. So you'll see better than that too. So Q-Chem, well, we probably won't change our defaults, but probably Q-Chem's default will remain the 2E4C, but I don't know, you can ask Kuan Yu at the end. But if you switch with just a single rem keyword in the input file to RI for energies and gradients, you get these large speedups. A new feature that I want to mention from one of our development groups is density-corrected DFT. And this is an idea put forward by Kieran Burke and co-workers over the past roughly decade or so, suggesting that in cases where DFT may fail, i.e. due to delocalization or self-interaction error, it's useful to do single-shot DFT calculations with a non-DFT density, in particular the Hartree-Fock density, because that doesn't suffer from delocalization error. Q-Chem has the analytic gradient for DC DFT, thanks to John's group, and you can read about it, if not now, then very shortly in JPhys Chemlet. And here's just a pretty picture from John and his students to show you how standard DFT delocalizes a hole artificially, whereas density corrected BLIP then of course gives you the localized hole that the density comes with and a much better relative energy. And similar considerations even for hybrid functionals, though they are not so susceptible to delocalization error. Okay, so that's the end of the first set of DFT related features. I want to now spend some minutes discussing interoperability. So Q-Chem as a 10 million line code kind of is not an island in the workflows of practical computational chemists. It already talks to graphical user interfaces, talks to workflow products like Atomate and other things, but we recognize that there's a need for improved interoperability. And so a major project led by Eric Bergquist and also independently by Andrew Gilbert is making significant headway on this. And we have, in fact, 2 new interoperability tools that are coming along at slightly different rates. They have very different kind of goals and very different levels of difficulty to achieve. The most ambitious of the 2 is the libarchive project, which is developed by Eric as one of his major projects at Q-Chem. And this has the goal of essentially recording the progress or documenting the progress of a Q-Chem calculation, however it goes, however non-standard, however varied the job specification, by writing an output file. And this is to try and then, and this is an output file in a standard format that will eliminate the parsing problem associated with standard formats like Malden or FCheck that are not machine readable, not that human friendly either, and rather scope limited. So we have been aware for a while that we need to do more on this. And so Eric has been leading the way here. by producing a self-describing Q-archive file that's stored in HDF5, and its schema-like hierarchical file structure defined in JSON, so these are industry standards, essentially will document the course of a job. And the first application is perhaps just an exemplar, and that's native IQmol integration to allow automatic discovery and visualization relevant quantities from not the limited checkpoint file, but the far richer Q-archive file. And then coming soon will be a Python package, and this is, I think, on the order of a year out, for reading Q-archive files with documentation auto-generated from the JSON file. Also soon is conversion of the Q-archive to MOL SSI's QC schema output format, if that interests you. And the vision is really to have Q-archive fully document the progress of a calculation, the provenance of data, and to allow restartability. So this is a very ambitious project that is coming to life. So Q-Chem 6.0.0 will write the Q-archive file, and if you are curious, you can look at it, and it's supposed to be quite readable because in fact it has HDF5 type format. We have a second archiving tool that is much lighter weight. In other words, this is designed now for easy interfacing and for a small, if possible, nearly zero learning curve. And this is co-developed by Albert from Shirin Faraji's group in Groningen with Andrew Gilbert of Q-Chem. And this Q-Chem archive concept is rather different than the QC archive just mentioned. There are two stages. One is an initialization step that declares a set of HDF5 data spaces. So this will determine the scope of the resulting HDF5 file and enables an absolutely minimal interface to go write that file. So for instance, this is writing the energy gradient in one line of code to the HDF5 file once the initialization is completed. So this is, as you can see, natural and convenient for creating a well-defined HDF5 output that might be needed by an external package that has, for instance, well-defined requirements in terms of the data that it needs to get from Q-Chem. So for instance, that data might be the energy and the forces on one or multiple states. And so our first example, this reflects the interests of Shirin Faraji's research group on QMMM and non-adiabatic dynamics. So this is a Q-Chem to PySurf interface that enables excited state dynamics external to Q-Chem. You can read about PySurf in this paper from Shirin's group here. And it's this is the first working example of Q-Chem archive. So this is less powerful and less flexible than libarchive. It doesn't have the same goals of targeting progress, provenance, and restartability. It has the goal of being lightweight and easy to use. So that's a second capability. So again, these two capabilities are going to allow greatly improved ability to restart Q-Chem jobs through libarchive, greatly improved capabilities to interface to Q-Chem from Python projects or even projects in other languages. So Eric Bergquist wanted me to mention that support for Julia, for example, would be provided, and so you can interface to the libarchive file from various languages. Other interfaces, even to exotic technologies, are available. So Anna Krylov's group at USC, with thanks to Yongbin Kim, have developed a Q-Chem to Open Fermion interface. So if you're curious to play around with the VQE, the variational quantum eigensolver, and use Open Fermion, you don't have to change your favorite quantum chemistry package to do that anymore, and you can read documentation and a manual at the website shown below. Okay, so that's interfacing. Now I want to turn to a major new piece of infrastructure. And as a retired sort of notionally retired procedural programmer, it gives me a certain twinge of sadness to announce that one of the last pieces of Fortran 77, or maybe even 66, in Q-Chem is steadily being eliminated by this project and being replaced by a thoroughly encapsulated, object-oriented, robust and thoroughly tested and updatable geometry optimizer. This will address many of our users' requests for improved geometry optimization features. And this is entirely new, as I said, and this is Peter McLaughlin's signature project at Q-Chem. He's one of our more recent employees, and this represents his major efforts since joining Q-Chem. This libop3 that he has generated gives the user lots and lots of choices. Choice of optimization coordinates, choice of optimization algorithms, far more than we have in the old Fortran 66 John Baker type code. It also meets the request from users for the a periodically recomputed Hessian for quasi-Newton methods. And in Q-Chem version 6.0.0, this is in fact our default optimization package for unconstrained optimization. And there'll be a lot more coming, and this will gradually take over during the version 6 evolution to, I think, manage substantially all aspects of geometry optimization. Well, here I am almost half an hour into the webinar, and I haven't shown you a Q-Chem input file yet. It's outrageous, isn't it? So here's a sample input showing some of the flexibility provided by libop3, in particular the recompute Hessian. And I just want to briefly mention that Peter, as mentored by Evgeny, has been doing extensive stress testing to make sure that when you begin using libop3, you'll have a good experience. So I won't say more than that. We've done probably more than 10,000 optimizations with libop3. The structures are equivalent. It matches or outperforms our old optimizer in key scenarios. All right, then what else? Q-Chem is coming closer to moving at the speed of light. I am excited to report, and that is thanks to developments in my research group at Berkeley, in particular Leo Cunha, a very talented graduate student, has implemented scalar relativity, and I'll show you some examples for core spectroscopy, but you can use the new Q-Chem scalar relativistic capabilities in version 6 to do everything from standard DFT through to wave function theory through to high-level correlation methods, all of which Q-Chem has in abundance. But I'm going to focus here on core spectroscopy, and it's a way to highlight features that we didn't really think were going to be a big part of Q-Chem 5, but emerged right at the end thanks to a great deal of excitement in my group around this. And this is because of the emergence of core spectroscopy as a topic of great excitement in experimental physical chemistry. If you excite a core electron to a valence antibonding orbital, the resulting spectrum is element specific because of the different 1s energy levels, but it's also site specific because of the different coupling between valence antibonding and core holes made at different spots in the molecule. So pump probe experiments where the probe is an X-ray photon in principle allow you to approach the experimental dream of watching a chemical reaction in real time. But you can only watch it if you know how to interpret the resulting spectral signatures. So this is how my group got into this, and I mentioned already that Leo was responsible for the relativistic stuff. Dip Taka-Haight, a brilliant graduate student in my group who's just starting a postdoc at Stanford now, was responsible for really our focus on OODFT. And to see why this focus is so useful, you can watch Dip's webinar from last year on this, or maybe it was even earlier this year. But the key thing is that time-dependent DFT exhibits really disastrous errors for core excitations, errors on the order of 10 to 20 volts. And And so while there have been heroic efforts to improve TDDFT, including led by the late Nick Besley, who tragically lost his life just recently, and was an important Q-Chem developer in the UK, you can see, though, that standard functionals are very inadequate. By contrast, you can barely even make out the errors associated with OODFT, this optimization of a spin-adapted configuration wave function with orbitals that are non-orthogonal to the ground state. You've got to zoom in a factor of 20 to see the errors in OODFT. They're so much smaller. So with standard functionals like the scan functional or our own omega B97X-V hybrid GGA, you get errors in these excitations that are these are giant excitations in the hundreds to thousands of volts, and we are coming down to errors of less than a third of a volt. But we, of course, if you're going to remove an electron from a core orbital, it's the core electrons that move closest to the speed of light. So that's where the relativistic connection comes in, and that's what we could not do before with any reliability. So, so Leo has implemented the spin-free exact two-component one-electron model that was, I think, originally suggested by Ken Dial in the late 1990s, and has gradually emerged as, I would say, the closest thing to a standard in relativistic electronic structure, relativistic quantum chemistry. And it's very nice in practice because this treats scalar relativistic effects through essentially a dressed core electron Hamiltonian, and then the rest of our conventional non-relativistic machinery proceeds largely unmodified. And this removes the need to make atomic relativistic corrections and enables us to do accurate core spectroscopy and anything else that we might like to do more accurately, all electron on heavy elements. So as one example, if you neglect relativity, the RMS error for scan in the third period elements across 20 small molecules goes from that amazing accuracy I showed you for the first row to relatively poor accuracy, because relativistic effects are rising with a polynomial power of the atomic number. And then scan with X to C, we're right back at the outstanding performance that that got us so excited back in 2020 to begin with. And that's just the data. Okay, so so then that's scalar relativity. I now want to say a few words about non-adiabatic couplings and a new dynamics code. This is also work done in my group. This is the postdoctoral research of Justin Talbot, who actually did his PhD with Ryan Steele in Utah, another Q-Chem developer, and then came to Berkeley to postdoc jointly between my group and Steve Cotton and Bill Miller. Hence the focus on non-adiabatic dynamics. And to make non-adiabatic dynamics more efficient in Q-Chem, we have, or should I say Justin has, rewritten the code. Scheme 1 is what we have in Q-Chem 5, Scheme 2 is what we have in Q-Chem 6, and there's a speed up of more than a factor of 3 with the same excellent parallel efficiency across all key pieces of evaluation of the non-adiabatic coupling. So these are examples for excited states of alkanes of differing sizes evaluated with TDDFT now and PBE0, so a hybrid functional in the 631G star basis, and old versus new, the gap is striking indeed. So this is something we're also excited about. And it's accompanied by new dynamics code. So I told you before about the interface to PySurf and external dynamics, but Justin, together with Steve and Bill, have put the latest version of quasi-classical, symmetric quasi-classical, or SQC dynamics inside Q-Chem, so you can run it directly. And this is just a picture of results from a couple of hundred trajectories associated with ultra-fast non-adiabatic relaxation in the proton transfer system, intramolecular proton transfer system, malonaldehyde, where you can see that there is a great S2 is the state pumped at time 0, and within about 50 femtoseconds, there's a dramatic population drop. And related to radiationless transitions, spin-orbit coupling matrix elements are also available, mean field in the 2-electron term, as a result of work from Anna Krylov's group at USC, and Justin himself is also doing spin-orbit coupling matrix element work. And there's much more. So I'm now going to flash through a bunch of other features that highlight contributions from of different that don't fit into the categories I've yet included. So let's start. From John Herbert's group, his group has contributed excellent real-time TDDFT code to Q-Chem, and that code has been extended to include complex absorbing potentials. A complex absorbing potential is something that just sucks up outgoing flux from a problem in which electrons may be ionized or become free. And so that's very important to, for instance, simulate attosecond electron dynamics in strong fields where there may be partial or even full ionization. And so you can read about it in applications to high harmonic generation in JChem Phys late last year, and applications to X-ray spectra. And John's group is a major Q-Chem developer, and so this is a nice way to highlight Q-Chem's real-time TDDFT capabilities and its latest enhancements in version 6. Another set of new features, Q-Chem has very strong coupled cluster capabilities, especially for excited states, where Anna Krylov's group is a recognized world leader, and more recently, Sonia Coriani's group from DTU has also joined forces as a Q-Chem developer. And again, it's great to see new development groups coming along, and so I wanted to highlight work from Sonia Coriani's group in collaboration with Anna's group on a series of really interesting chiroptical properties, optical electronic circular dichroism for ground and excited states, and X-ray circular dichroism, and optical rotation dispersion. And this is all connected to the optical rotation tensor, in which can be evaluated, its power can be evaluated in various gauges. It's got real and imaginary parts. That's one thing. A second thing from John Herbert's group, again, so Ohio State, is improvements on the restricted active space spin flip method that was originally developed in my group around 2009-10 and has been greatly improved in its implementation in Q-Chem by David Casanova's group at ICABASC and also Paul Zimmerman's group at Michigan. And John teamed up with Paul's group to add implicit solvent to RAS spin flip, and they have done a beautiful application that I don't have time to go through here to the generation of multi-excitons in singlet fission. RAS spin flip is a great method for problems in which there are up to 4 unpaired electrons because it's able to entangle 4 electrons quite efficiently. Okay, so I'm getting towards the end here. I want to leave time for questions and discussion. I want to finish by talking a bit about what lies ahead. So, so most of the things that I told you about are either in version 6.0.0 that's being wrapped up at the Pleasanton office right now, or are going to come very soon after. But there are some things that lie a little further ahead, and they're kind of neat, and so I want to tell you about them. One is from Yu Zhang at the Q-Chem office. He is busy completing a customer, a much asked for request, which is for vibrational circular dichroism. So, so Yu's implementation is more or less done. We're in the debugging and prototyping phase, and Yu anticipates that this will be available later this year, and I don't really need to belabor the importance of this. So this is a sort of missing feature in Q-Chem that's coming along. A feature that is rarer is an in silico NMR lab that's been in development in my group for a couple of years, and this is a potentially exciting, something I'm excited about, and I hope you may be too. The idea is to, instead of doing analytical derivatives for magnetic properties, which requires then second derivatives for almost all interesting properties, And analytic second derivative implementation is a pain in the neck. So you can do it for DFT, maybe for MP2 with great difficulty. We don't really want to ask any students or postdocs to do it for other methods. So it seems interesting to mimic the experiment and apply finite magnetic fields and finite nuclear spins, and then evaluate the property of interest by finite differences. That's what the in silico NMR lab is for chemical shifts, magnetizabilities. They're both done, and coming relatively soon afterwards will be scalar couplings. There's a lot of complexity involved at the outset, so there's a high induction barrier. You need complex matrix elements because the Gaussian atomic orbitals become complex in a magnetic field if you properly apply the gauge factors necessary to ensure gauge including atomic orbitals. You also need then complex molecular orbitals, so your Hartree-Fock is not restricted or unrestricted, it's complex restricted or complex unrestricted. And then if you do correlation, that also must be complex. But we built those tools over several years for other reasons, and because we have the power of object-oriented design here, we can reuse those things for this in silico NMR lab. And so after we paid the startup cost, we'll be able to do a whole bunch of NMR-related things in the near future that we can't do right now. So here's a little catalog for you, and the first release should be later this year. So anyway, that's something I'm excited about. I want to acknowledge the team of people in my group: Jonathan Wong, Brad Gano, Xiao Lu, Jiaoshu Liang, Junho Lee, Tim Neudecker, Nay Stouch, and Adam Rettig, who've made this happen. Another really exciting brand new project is a new from the ground up periodic boundary condition code in Q-Chem, and the driving force behind this is Junho Lee. And if you've not already heard of Junho, you'll hear more about him in the future. He was a brilliant student in my group, now a brilliant postdoc in David Reichman's group at Columbia, and he will start a position as an assistant professor of chemistry at Harvard University next year. And Junho really has been the mover and shaker behind this in terms of the academic side, teaming primarily with Xintian and also Shannon at Q-Chem. And the idea is we are building a code that is Gaussian based in the atomic orbital sense, and has some special condensed matter characteristics to deal with periodic unit cells. So there will be auxiliary basis sets that can be plane waves with pseudo potentials. There's an all electron capability under development thanks to Adam's thesis work. And we've already completed exact exchange, including range separated hybrids. We support K-point sampling and of course gamma point, and we can do total energies and band structures, and the gradient is under construction. The first publication is out, and the second publication is under active construction, led again by Junho, and look for a first release of Q-Chem's PBC capability sometime next year. We don't quite yet know whether that will be a separate product or how we'll do it, but it's an exciting another exciting thing that will be available to the Q-Chem community soon. Okay, so I'm going to begin to wrap up here. Let me remind you that qchem.com is where you go for all the information. You can also watch many other webinars other than this one if you find yourself with a little spare time. Please browse the manual or browse online. And I've told you a bunch of stuff, but there's actually a whole bunch more that I didn't tell you that's top secret. Well, as top secret as academics and Q-Chem scientists can be, I guess, that will appear in later versions of Q-Chem 6. So again, the rolling annual releases means that what you see in version 6.0.0 is the dawn of the next generation, and the daylight will be really something to see. So, and finally, without giving anything away, I want to hint that there is an entirely new product also in development that is that you'll hear much more about pretty soon. So please stay tuned. It's going to be a very exciting rest of 2022 and onwards with Q-Chem. So let me remind you how to reach Q-Chem if you're interested in ordering or renewing Q-Chem maintenance plan or support, these are the contacts. And let me acknowledge once again the Q-Chem team. To me, again, it's a pleasure to represent the Q-Chem community here today, and the teamwork and the passion that the 8 scientists and our 2 office managers display is an inspiration to me, and I want to thank them all, particularly Evgeny, whose fingers and inspiration is in everything that's done at Q-Chem. And good leadership begins at the top. So Anna Krylov is Q-Chem's president. She has done a great job since taking over from Q-Chem's longest serving president by far, Peter Gill, who's still on the board and still active. And we welcomed Shirin Faraji to the board relatively recently, and she's an active participant. And John and Hillary are key longer term board members. You've heard a lot about John's work. Hillary is in a way a direct link back to Q-Chem's roots in Gaussian as a breakaway from Gaussian, where John Popel joined us early on. I was a student with John, so was Peter was a postdoc, and so the quantum chemistry DNA is alive through Hillary, who gives us wise financial advice. Her specialty is finance. I want to thank my research group. I want to thank the Q-Chem development community for the trust that you put in us to protect and advance your developments. Your developments are what make Q-Chem 6 possible. And then I'd just like to thank everyone who's joined the webinar today for taking the time to do so. And I'll stop there.
Thank you, Mark. Thank you for putting those various features in an organized and informative talk. And we got several questions here. So first one, can you comment on the parallel efficiency of OMP and MPI versions?
Sure. So Q-Chem is primarily an OpenMP parallel code. So I spent quite a while talking about the efficiency of DFT because DFT is the predominant use case. But we have also very good OpenMP efficiency for MP2, the MP2 gradient, for couple cluster, the couple cluster gradient, for equation of motion couple cluster, even for our strongly correlated methods that I didn't mention, the adaptive selected CI SCF is adequately parallel as well. So OpenMP parallel-wise, we are a very strong code. We are not a strong code yet in MPI. We abandoned MPI over a decade ago, or largely stepped back from it. We have a skunkworks project to go back to MPI for the kind of mixed shared memory, distributed memory paradigm, but it's not at the stage where I can reveal too much about progress or precise timeline, but that is on it. So I guess a way to summarize is that OpenMP is really well polished, and MPI is returning. I didn't mention, but I could mention that GPU capabilities exist through the Brian QC plugin for Q-Chem, and that is might be of interest to people who've gone for high-end GPUs. Q-Chem can take advantage of those through the mixed GPU-CPU mode, and then that's relevant to things like the new NERSC supercomputer, where you can see where, as I showed you early on, each node is a GPU-CPU hybrid. So maybe that's a few comments to respond to the question.
Thank you. Actually, our next question is related to GPU. So does Brian QC support the new RIJK engines?
I don't know.
Yeah, I guess I can answer this one. So for now, no RI is supported in Brian QC, but they're on the feature requests have been where it's under development. So next questions. So does the SQC dynamics has been documented in Q-Chem manual yet?
It will be part of the 6.0.1 release. So that's, you know, I didn't talk about Q-Chem's development process, but because it's time-based, the check-in queue for developers closes at a particular magic date. I've forgotten, maybe Quan, you can tell us roughly when it was. I feel like it was late February or early March or something. And so Justin's code did not quite make it in to that check-in. So he will check in as soon as the queue reopens, and that will be for 6.0.1, whereupon it will be fully documented both in code and in that. Yeah, so that should be in user hands by the August release.
Thanks. Next question. Are there plans for DFT-based ECD or VCD? I think we already talked about that. So Eugene, he's working on the DFT-based ECD and VCD. So it's coming soon, I would say. Sorry, yeah, go ahead.
No, that's okay. I was just going to say that it could be that other properties will come out of the in silico NMR lab, because finite fields and finite nuclear spins allow you to evaluate quite a range of other properties as well.
And I guess that's a follow-up question. Are there plans for IQmol to support the visualization or analysis for the ECD or VCD?
Yeah, I think that we would have to discuss. I think, I'm not sure if you is online to speak to that, but obviously IQmol and Q-Chem development go hand in hand. You know, we haven't, you know, if you're new to the Q-Chem community, IQmol is our free and open source visualizer optimized for Q-Chem and co-developed, you know, developed the principal developer, Andrew Gilbert, is a Q-Chem employee. And so each major release of Q-Chem and each annual update is synced between advances in IQmol and advances in Q-Chem. So as soon as use capability is ready to go, I expect that he will be consulting with Andrew to get visualization support.
Okay. Our next question is, do you have plan to add something like atomic valence active spaces for CAS-SCF calculations?
Well, Q-Chem does have both conventional CAS-SCF and the powerful, though not entirely easy to use, FP-SCF, and so those permit kind of traditional selection of active spaces. I'm not completely sure, you know. So by atomic active spaces, you mean things similar to what Toru Shiozaki maybe worked on? So I think the answer is no immediate plans, but if you're a customer and you're interested, please let us know through the Q-Chem forum about your interest.
Thanks. So our next, sorry, I was reading the question, hard time reading this question. So how, do we have plan to include the Stefan Griben's XTB code for QMMN for explicit salvation?
Interesting question. Well, we have interest in XTB and maybe even alternative parameterizations, and there is a project underway in my group that is a Q-Chem integrated XTB that uses our SCF solvers. So there is activity there. that would then be a kind of QM type of mixed modeling that might be appropriate for that. That's not a near-term future, but it is not a near-term feature, but it's definitely within the Q-Chem 6 generation. So in other words, that's one of the projects I didn't talk about that's underway.
Thank you. Okay, I'm gonna tend to close the webinar. First, I would like to thank Juan again for giving this wonderful talk, and it's really excited to see new features in Q-Chem 6. And also want to thank all the attendees for your listening. And if you're watching this from YouTube, feel free to send your questions to me, or if you have questions later, also feel free to send me the questions. Yeah.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.